If you're going to write an equation for a line, what two things do you need? Slope and a point on that line.
Just kidding.
I'm telling you at this time that you have the x-intercept and the y-intercept of -3. Okay, so pick up where we left off with this sheet, this one from the other day. Just finishing off the last two problems on there. Slope and a point that exists on the line. What point would you like to choose to use? Sure, we could use 0, -3. Very good. So I need to calculate the slope. Any thoughts?
Yes. No, that one.
Formula for? You need 2 points. So this point here is 0, -3. What's that coordinate? 5, 0. Can you now find the slope? -3 minus 0 over 0 minus 5, and I get positive 3/5. Is that enough information to now write it? True or false? I need to use point slope form. Why? Have your y-intercept. Save yourself some work, folks. Pizza cake upside down. You try the last one by yourself. Go. Compare with a partner. When you write an equation for a line, what two things do you have to have? Slope and the point. Can somebody tell me what would be the slope of the new line? -1/3. We then must use -9,1 in order to determine the slope-intercept form. Y minus y1 is equal to m times x minus x1. We distribute the -1/3. Y minus 1 is equal to -1/3 x minus 3. Add the 1. Y is equal to -1/3 x minus dos, which is Spanish for 2. Are we all good? Excellent. That's a basic review into some functions and writing equations for lines and things of that nature. I know that some of it will stick with you better than others. We will continue to review things as we move along. I promise I will dedicate a significant amount of time to a trig review as well as an exponential logarithmic review at later times. Take out your new packet that we are at within our notes, and let us start the problem of calculus. Your group didn't get one. I would complain. I would say, I've had it. He doesn't like us. No more Mr. Mace Dog. Very good. If you will see him, yes. Nope. And so there we are. It is the question of calculus. Calculus begins with really two ridiculous questions, and we're going to encounter one that is going to be the broad study of our first semester, okay? And the word calculus comes from the word calculate. It means the ability to calculate the infinitely large and the infinitely small. You are used to subjects like geometry and algebra, right? So what is calculus in comparison to that? I would say calculus is almost like, it's more like a trigonometry or a Pythagorean theorem. It's this thing that we learn that has power. Like a squared plus b squared equals c squared. That's powerful, is it not? So there's things that you learn in calculus, namely derivatives and integrals, that have power to them. They allow us to do amazing, amazing things. But we have to show you what those are first. And it comes with this idea, the tangent problem. Given a curve with a line tangent at a given point on a curve, what is the slope of the tangent line? Now, we wrote it down, but just because we wrote it down doesn't mean we understand what the heck it even means. So let's look at an example. It says given the function x squared plus 1, Find the equation for the line tangent at 1, 2. So what does that shape look like? Parabola, shifted up 1. Very good. Now, it's saying find the equation for the line tangent at the point 1, 2. Does everybody agree that it passes through the point 1, 2? How do we know it passes through the coordinate 1, 2? Because if you plug in 1, you get 2, right? 1 squared is 1 plus 1 is 2. So what we're wondering is if we were to draw a tangent line, meaning that the line crosses at just one spot, namely at that point, the question is, what is the slope of that line? What the heck is the slope for the line? That's a really good question, isn't it? And the reason why it's difficult is because there is only one point. You need 2 points. For slope. Right? You need 2 points for slope, don't you? So what is it if we have 1 point? That's tough. And so we start to encounter this huge calculus problem. Unfortunately, we're going to get really good at solving this problem, and you're going to be able to understand it today. We have this point P, we'll call it. And I don't know the slope of the tangent line. There's just 1 point. So therefore, what I'm going to do is I'm going to create a second point. Because in order to find slope, we need 2 points, right? So I'm going to move over 1 spot to 2. And we'll call that point Q. The red line is what we call the secant line. The blue line is what we call the tangent line. Our goal is to find the slope of the blue line. Is the slope of the red line greater or smaller than the slope of the blue line? Greater. Everybody agree? You can look at it and say it's greater. Would you agree that the red slope of the red line is not the same as the blue line, but it's similar? Like it's somewhat close? Yeah? So let's find the slope of the red line at this point. Let's find the slope of the secant line. I need 2 points, right? What's this coordinate? 1, 2. So you can see we have one coordinate, which is 1, 2. Now I have point Q, and point Q sits up here. It has an x value of 2. What's the y value? 5. How'd you get 5, Raiden? He plugged 2 into the function. 2 squared is 4 plus 1 is 5. So 2, 5 is the point for Q. Is everybody clear how he came up with the y value? Very good. So now I'm going to calculate my slope. I will take y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. notice that I get 3 over 1, which is 3. Is 3 an overestimation or an underestimation? It's an overestimation. Suppose I wanted a better estimation. I don't like that I'm off by however much we are. What could I do to point Q to come up with a better estimation? Where could I move it? Down, right? If I moved Q closer, wouldn't that give me a better estimation? Like instead of going from 1 to 2, what if I went from 1 to say 1.5? Would that be better? What if instead of going to 1.5, what if I went to 1.1? Would that be better? Yeah, that would be better, wouldn't it? Let's do another one together, and then I'll divide you up in groups of 3. So suppose instead of going all the way over to 2, suppose I went to 1.5. You know, as I slide Q to right there, wouldn't you agree that the slope of the black line is much closer to the slope of the blue line? Those are getting close, aren't they? So hopefully we come up with a better estimation. All right. We still have our point, 1, 2. Our second point, we have an x value of 1.5. How do we find the y value? Plug it in. 1.5 squared is 2.25. Plus 1 is 3.25. Do I have enough information to now determine slope? I do. Y sub 2 minus y sub 1 is 1.25. X sub 2 minus x sub 1 is 0.5. 1.25 divided by 0.5 is 2.5. We all said that this would be better, right? It would be better. We're going to get closer, right? Looks like we went from 3 down to 2.5. I want you right here, this row, this group of you guys, I would like you to choose an x value of 1.1 and see if you could come up with the y value and the slope. You guys right here, I'd like you to choose an x value of 1.01, find the y value and the slope. And you guys over here, I'd like you to use x value of 1.001. Find the y value and the slope. You will want to use your calculators. Check with your partners once you get a result. Good luck. You're going to do a great job. Nice job. Now looking at your calculations, but again, we just plugged in a y value, found the slope. The slope should be 2.1. Are we good over there? Are we right? Okay, middle group, you should come up with 2.01. Are you right there? And then last group, 2.001. Are we right over here? So this is the really important part. Everybody look at the data. When point Q was a full unit away, the slope was 3. You drew it closer. When you got closer, it went to 2.5. When you went to when you moved it closer, you got to 2.1, 2.01, 2.0001. So again, the word calculus means to calculate the infinitely large and the infinitely small, meaning infinitely close. So if we were to move point P and point Q infinitely close together, what do you think this number is trending to? 2. Does everybody agree that the data suggests that you're headed towards 2? Yes. You have just done what we call calculate a limit. Talk to that person next to you and identify, have you watched the movie Mean Girls? And if so, what do you remember from it? Go. Today you want to be able to learn what limits are about. If you flip it over, it says the solution to the slope of the tangent line problem can be expressed as this. And it's going to take you a while to learn what this means, but I want you to understand that we had point P be the following. It was the coordinate 1, 2. And we had point Q be the following. Well, it was an x value, and then you plugged it into the function x squared plus 1 in order to get the y value. I mean, that's what you were doing, right? So instead of continuing to plug in numbers, let's just look at this. And if you had y sub 2 minus y sub 1, that's the top piece, right? And on the bottom, you would have x sub 2 minus x sub 1. That's the bottom piece. And really what it means is this, in plain terms, as Q moves toward P, the slope approaches two. As Q moves towards P, the slope approaches 2. And so we say the limit of that is 2. Limits are what formalize calculus. Calculus was developed in the year 200 BC approximately by a guy by the name of Archimedes, arguably the greatest mind ever walked the face of the earth. But it wasn't formalized until the year 1600 with Isaac Newton and others who were able to put that piece together. And so you don't have this page, do you? Yeah, I picked up something I wasn't supposed to have. Don't worry, you have the top part. Just give me a second here. Okay, you now have a box that looks like this, correct? Very good. Then that's what we are going to move towards. There's a formal and informal definition of a limit. Informal definition of a limit as x approaches a of the function is equal to L. What that means is this. As the x values or inputs approach A being a number, the y values outputs approach L, the limit. So what we want to do is we want to calculate limits today. We want x to approach a value, and we want to see what the y value approaches. The limit is a y value. It's the output. Okay? Please take out your graphing calculator. Let's get some of those kinks out of the way. If you don't have it, you can follow along with what I have, but please press mode. Some of you guys are working in different modes. The last thing we left in this class, I think we're working in parametric and polar mode. Please press mode and make sure you're on function. Second of all, if you go up to radian, make sure you're working in radians. 99% of the time this year calculus will be working in radians. We will not be working in degrees. And finally, as you go over to y equals, let's type in this function, 0.5 x squared minus x plus 3. That's my function. Is everybody okay with the function? We're going to have the x value approach 2. Okay? First, let's just get a picture of the graph. We're going to all view in the same window. So let's press zoom standard, which is zoom 6. And that brings us to a standard viewing window. So the idea in this situation is that we're going to approach an x value of 2. We're wondering, what does the y value approach? What does the y value approach? Okay. So we're going to do this a couple ways. I want you to understand that there's really 3 ways that we're going to look at this data. We're going to look at a graph, we're going to look at a table, and we're going to do it algebraically. You need to be able to do all 3. So don't think I'm just trying to have fun with you by confusing you. You have to be able to do all 3. Okay? So here's some operations on your calculator. And I'm trying to think of all the operations because last year we didn't do a calculator review. Okay? We're going to try to build in those calculator options for you. The first thing we're going to do is press trace. And as you trace, you can see x values and y values. What is the x value that I'm moving towards? 2. Very good. I'm moving towards 2. Let's move towards 2. Look at the y values as I'm moving towards 2 for x. Here I'm getting close. I'm at x value 1.9. Here I'm at 2.9. I move past 2.3, 3.3. If I move back down one, I've got 2.1, 3.1. Anybody want to guess what the y value is? Probably 3. Yeah. That's a graphical look. Let's try a different look. Let's look at a table. Please press second table set, which is second window. I don't care what your table start is at, and I don't care what your delta table or change in the table is at. What I do care about is your independent variable. Please turn your independent to ask. Please take your dependent variable and set it to auto. And that's probably what you'll want it to be for the entire year. And by the way, if you'd like to rent a graphic calculator here, you sure can. We will contact Ms. Hanson if you'd like to have one. I'll bring in some forms tomorrow. And now I'm going to go to second graph or table. And now you should be able to type in values. I'm going to get close to 2. Can somebody think of a number close to 2? 1.9. 1.9. Can somebody think of a number that's even closer to 2 than 1.9? 1.99. How about 1.999? How about 1.9999? Can you see that the x values are getting closer to 2? What's happening to the y values? They are getting closer to 3, aren't they? And so therefore we could say that the limit of this function is equal to 3. Now, it just so happens in this situation, if you plug in 2, you get 3. That's not the definition of a limit. That's not the definition of a limit, what you get when you just plug it in. It's what it's approaching. So please just understand that this is your first example. Okay, next one, square root of x plus 4. What does it look like? Good. Shifted to the left 4 units. And x is approaching what value? 0. So at 0, we're really wondering what is that height. Take 20 seconds to talk to those around you, see if you can figure out what that limit is. Go. So your plot is stuck on, so we're going to take that off. Oh, and then your mode, again, so you're stuck in a parametric, you're going to go down to function. Anybody got a thought? 2. It is 2. Notice this is a very nice behaving function. You can see that the height here is 2. And so if you just look at it, if you approach from this direction, the height is 2. If you approach from this direction, the height is 2. If you weren't convinced, you could go into your calculator and type in, I like to grab my square root function right here, so second square root, x plus 4. And once I have that, as I go to the graph, you see we have this piece. As you go to the table, you can type in numbers that are close to 0. What's a number close to 0? 0.1, 0.01, 0.001, 0.0001, so on and so forth. You can see that the values are heading towards 2, aren't they? Okay, excellent. And so if you were to plug in 0, you get square root of 0 plus 4 is the square root of 4, which is 2. So there are times where you can just plug it in. Question? A for the day. Excellent question. If you notice, if I were to plug in this value of 0, notice how it just gives me 2. So why not plug it in right away? We have to, the limit has to be approaching it. We must get closer to it. We don't want to look at just at that one spot. We want to get closer to it. Why? Because this one right here, Miss Leah. Let's flip it over, folks. Or I'm sorry, I'm flipping over, you're not. h of x is, or are you?
Yeah, we are.
Oh, so we're on the same thing now?
Yeah.
Okay, h of x is x squared minus 3x over x minus 3. Watch what happens if we plug in, what is the value that we're approaching? We're approaching 3, so let's see what happens when we plug in 3. You get 9 minus 9 over 3 minus 3, which means we get 0 over 0. Does anybody know what 0 over 0 is? Actually, it's what we call an indeterminate value. When you have 0, anything over 0 is undefined unless it's a 0 on top. That's an indeterminate value. We don't know what 0 over 0 is. In fact, much of calculus is based around the idea of trying to find out what 0 divided by 0 is. So let's discover what 0 divided by 0 is. Let's take a look at this graph. Go to your calculator. Go into y equals. Let's take parentheses so that we get the top graph, x squared minus 3x divided by the bottom, which is x minus 3. And I'm going to zoom standard, zoom 6. There we have it. That's my graph. Okay? What does it look like? It looks like a line. But it's not a line. It's a line that has a gap in it. And I'll show you why. Watch. If I zoom decimal, zoom number 4, watch my graph here. Oh, did you see it? See it? Look at that. So if I press trace, this is really cool. You follow along, you're like, oh, 0.3, 0.3, like it's staying the same the whole time. But when you actually get to that value of 3, 2.4, 5, 6, 7, 8, 9, and boom, it just vanishes. Like you got x value 3, but you got no y value. And then you advance one more, and boom, 3.1, 3.1. So it's a function that has a hole in it. In fact, a lot of the limits that we're going to look at are functions that have holes in it. We want to know what's the height at that spot. Can somebody tell me, as you go through this, what as x approaches 3, what's the y value approaching? Yeah, it sure is. But we can't tell that by just plugging it in, can we? And now we get to my favorite one. We go to my function, I type in sine of 1 divided by x. And I'm going to choose to zoom in a standard window. Ooh. Kind of tough to draw that graph, isn't it? What's the x value approaching? 0. Let's zoom in. Zoom. We're just going to do a simple zoom in. Let's see what we get. Still hard to tell, isn't it? Let's zoom in further. Just watch mine for right now. I still can't see exactly. I'm going to zoom in again. Maybe we'll get a better view now. I wonder how far we could go. What? It's a barcode function. Ah! Insanity! Okay, I'll draw the graph. Yeah, so like who's a Hy-Vee checker outer person? Who we got? All right, could you bring like a scan tool tomorrow? We could like try that. Actually, better yet, next time you go to the store and you go to check out, bring this with and see what it charges you. You know what I mean? Yeah. You might get lucky. It might be 3 cents. It also might be $300, right? And so maybe you just try it. You just try and you're like, uh-oh, I didn't like that price. So I'm gonna try a new price. You just zoom in until you get the price that you like. You know what I mean? So maybe that's it. This is called the barcode function. And when the graph does not produce for you what you want, maybe you could go to the table. So I'm going to approach an x value of 0. So look at what I've typed in. I've got 0.1, 0.01, 0.001, and look what happens. I'm at like negative 0.5, then another negative 0.5, then a 0.82. If I do 0.0001, I get, now it jumps to negative 0.3, 0.00001. If I do that, then now I'm back to 0.03. Does it ever seem like it really tends towards a certain number? In fact, if you plug in 0, you get that whole error piece. The limit does not exist. There are times that we have limits that exist. There are times that we do not. So our goal is to get through this piece, and we're right about there. Good job. So calculus has big ideas. The first day you see it's going to be a longer kind of lecture piece, and tomorrow you can get more practice on your own. It says one-sided limits. If we have the limit as x approaches 3 from the left, we put a negative sign up there so that we know we're approaching it from the left-hand side. If we are going to do a right-hand limit, we do limit as x approaches 3, and we put a plus sign up there. It means from the right-hand side. So when the plus or minus is up at the top, that's what we use to delineate the right and the left. And using this piece, you can now calculate limits. This will be the first part of your assignment. You'll be given a graph, and you'll want to know the limit. Look at the first question. What's the number that we're approaching? Are we approaching from the right or the left? We're approaching from the left. So I have negative 4. I'm going to approach negative 4 from the left. So what is the output approaching as I get really close to negative 4? What's that height approaching? 3. Now I'm going to approach negative 4 from where? From the right. I'm going to approach negative 4 from the right. As you approach negative 4 from the right, what's that height approaching? Negative 2. See how it's different from the right than it is the left? Now what am I approaching for C? From the right or left? Left. So we approach negative 1 from the left. What's the output? What's the height approaching? 4. Now I'm going to approach negative 1 from the right. What's the height approaching? 4. Those happen to be the same, don't they? Sometimes they're different, sometimes they're the same. What's the next one that I'm approaching? From the left or right? From the left, approaching a height of? From the right, 5. What's different about letter G? If it doesn't have a right or left, it means the limit as a whole. And in order for the limit to exist, the left and right must be the same. Are those the same? So therefore, the limit does not exist.
Can you say that again?
Yes. In order for the limit to exist, it must be the same from the left as it is from the right. And that's where we'll pick up tomorrow, is seeing as you guys will get a lot of time to practice tomorrow in class on your limits assignment, okay? A lot of time to practice tomorrow on your limits assignment.